Good morning everyone. I am Ning Kong from Bihang University. The title of paper is Interactive Animation Generation of Virtual Characters using Single RGB D Camera. This work is cooperate with Jun Xian Bai, Jun Pan, and Hong Qin from Stony Brook University. I will introduce our work from 4 aspects. The rapid creation of 3D character animation plays an important role in virtual reality applications, especially in game industry and film industry. Many companies use optical capture systems to capture human motion, but these systems are expensive and complicated. They are not useful for household consumers. An interesting device is RGB D camera. RGB D camera can also capture human motion, and it is practical to use in home. So, a prevailing idea is to capture the motion of real human, and generate an animated character simultaneously, using single RGB D camera. When using single RGB D camera, there are 3 major challenges. First, how to improve the stability of tracking for human motion, based on single RGB D camera. Second, how to quickly retarget the human motion to virtual character, including humanoid and non-humanoid models. Third, how to enhance the quality of motion retargeting for real-time applications. Several works have investigated the potential of single RGB D camera. Bago used a course-defined process, on multi-resolution 3D body, to estimate the 3D geometry and appearance of the human body. Lu employ a real-time probabilistic framework, to enhance the accuracy of live captured postures. He used Gaussian process model to leverage the position data, obtained from Kinect and optical system. Yet employ metaballs for the pose, and shape estimation for articulated objects. Wang propose an local to global hierarchical optimization for motion tracking. Although many works have been proposed, they seldom consider the animation generation. In this paper, we develop an interactive framework for stable motion capture, and animation generation based on single RGB D camera. Our contributions can be summarized as follow. First, we propose an adaptive filter, to estimate the rotation angle and direction of the user, using a single RGB D camera. Second, we design a practical motion retargeting method, for humanoid and non-humanoid characters. Third, we devise a motion refinement technique, based on inverse kinematics, which can enhance the performance of target characters' motion. Now, let's introduce our system details. This figure illustrates our framework. Our framework uses single RGB D camera to capture human motion. Then we design a data filter, to estimate the turning angle and turning direction for the human body. Then we employ a quaternion-based method, to retarget the motion to 3D character. To improve the animation quality, we set up several constraints to the character. Let's first talk the data filter. According to our observation, following 2 cases often appear for most applications. One is the user facing the camera, the other user turning around. So we focus our filter to handle these 2 cases. We take the joints extracted by Kinect SDK as inputs. In many cases, the joints are incorrect, especially when the user is turning around or performing actions on his side. These errors may happen due to self-occlusion. The data filter is designed to improve the captured result. Here, I will introduce the details of the data filter. This figure illustrates the all process of the filter. The inputs include 3 parts: shoulder spacing, hip spacing, and face rotation. The final estimation is a combination of these 3 parts. We choose shoulders, hips, and face, because these joints are fixed for most cases, when human is turning around or performing actions. Taking shoulders spacing for example, after we get the spacing, we first compute 2 thresholds. These thresholds are used to detect whether the user is facing the camera or not. The thresholds are computed using the following equations. In Dmax equation, Wf is the proportion of points facing the camera in the motion curve, Wt is the proportion of other states points, Uf and Ut are the numbers of points facing the camera and points in other states. Bf and Bt are the sets of frames, in which the human body is facing the camera or in other states. Li and Lj are the values of shoulder spacing. The value Dmin is calculated in the same way. Dmax and Dmin are used to detect whether the use is facing the camera or not. In this figure, x-axis denotes the time, and y-axis denotes the spacing. If the spacing is larger than Dmax, we consider the human is facing the camera. If the spacing is smaller than Dmin, we consider the human is turning around. Then we use gradient retention to smooth the motion curve. Since the turning angle of body is related to the length of bone spacing, if the vibration is not processed, the final animation will be degraded. Gradient retention aims at removing noises from the motion curve and reducing vibration. In each frame, we add compensation to remove the vibration. L-start and L-end denote the length of shoulder spacing at the start frame and the end frame. After we get Dmax, Dmin, and L-loss, the next step is to calculate the turning angle. The estimation is computed using the following equation. The function of this equation is to convert the length to the turning angle. The process of estimation from hips is the same with shoulders, but the parameters are different. We found the best performance when Dmax equals 0.17, and Dmin equals 0.05. We use Kinect SDK to obtain the estimated turning angle from face. Through our experiments, we found 2 setups best fit the cases. Next, I will briefly introduce the estimation for turning direction. The turning direction is estimated through the last frame direction, the depth of left shoulder, and the depth of right shoulder. This step is to detect whether the human is turning left, or turning right. The algorithm is listed as follows. Now let's move to the motion retargeting process. Our framework is able to animate 2 types of characters, humanoid character and non-humanoid character. For humanoid character, we transfer the joints rotations of human to the character in a straightforward manner. The first step is to construct a skeleton hierarchy. We define joints on the original model similar to the human skeleton. Then we connect the joints to construct a skeleton structure. The second step is to calculate the rotation of each bones. We compute 2 vectors for each joint, one is pointing to the parent joint, and the other is pointing to the child joint. Through these 2 vectors, we can get the rotation axis using cross product. The angle is get using cosine. Then we write them into quaternion manner. The rotation is transferred to the character using the following equation. For non-humanoid character, we need to classify the action, then we animate the character using stored data. We train a SVM for video sequence offline. Then we use this SVM to classify the action online. After the action is correctly classified, we use stored data to create the animation. The classifier contains 3 steps. The first step is to determine whether it is a whole body movement or an upper body movement. The second step is to determine whether it is a movement containing 2 hands or single hand. The third step is to determine whether it contains gesture information. The final part is the constraint. Our quaternion-based method may contain artifacts like foot skating. We define translation constraint to remove the artifact. We calculate the offset from the root joint to the ground, and add the offset to joints in the upper body. When human squats down, the feet of character will be floating without the translation constraint. Also, if the user jumps, we will add the offset to the whole body. Moreover, we define limb constraint to refine the animation. Occlusion may appear and degenerate the animation. So we employ IK to remove the artifacts. Each character in our database has 20 joints and 17 bones. We set up 5 IK chains in the character. As shown in the figure, we define a waist chain, 2 hands chains, and 2 feet chains. The third part is the results of our experiments. Our framework is implemented in Unity. All the experiments are tested on a desktop with i7-6700 CPU. We select several CG models from Adobe, which include humanoid and non-humanoid characters. The experiments are divided into 2 groups, single user and multiple users. We test our framework in 4 scenarios. Next, I will give specific explanations for each task. As shown in the picture, our framework can retarget the captured motion to characters, with different sizes or structures. These characters have similar skeleton structures with real human, but the length of each bone is different. We selected 8 actions and some actions have self-occlusion. It can be seen that these actions are well retargeted from real human to virtual characters. This is a user's action to raise the arm and foot. This is a motion of bending and sitting. This is a set of human side-to-camera movements. Here, the user lifts his arm and squats down. We also compare the action of turning around. As shown in the picture, 3 cases are enumerated, including only retarget, retarget and filter, retarget and filter and IK. When the filter and IK are disabled, all results are incorrect. It cannot identify the whole process of the human body turn. After the filter is enabled, the rotation information of human body can be well captured. The rotation angle of character model is consistent with the angle of the real human rotation, but some poses are incorrect. If both the filter and IK are enabled, the transferred poses are the best. The posture solved by IK can be used to calibrate the pose of character model. Our framework provides user a real-time interface to control virtual characters, and interact with virtual environments. As a simple example, we developed fitness game as shown in the video. In this application, a single Kinect camera is employed to capture the motion. We predefine the reference motion, and animate the virtual character to instruct users. Through parallel processing, we can achieve motion retargeting from multi-person video. When more than one person appear in front of the camera, we handle multi-person motion data in multi-thread to ensure the real-time performance of the system. We transfer the motion from real human to virtual characters in a straightforward manner. Here we give the effect of motion retargeting from different angles. In our framework, both humanoid and non-humanoid characters are able to be animated. Here is the effect of driving non-human models. We compared our method on a group of postures, appeared in Liu's work. Our method cannot solve the turning problem very well at present, but in the case of the side view, our retargeting posture is closer to the real human. Moreover, we record the motion curves of human and virtual character. The red curve is the human motion captured by OPTI track, the green one is captured by Kinect, and the blue curve is the motion of target model animated by our method. After the comparison, we find that our method has less vibration and is closer to real motion curve. In the last part, I will talk about the conclusion and future work. In this paper, we develop a real-time framework for producing virtual character animation, using single RGB D camera. Our framework is capable of handling complex human motions like turning around. However, there are several limitations of our method. First, our method is dependent on the accuracy of the input joint information. The missing key points in the capture stage cannot be restored in our final result. Second, the influence factors are set manually at present. It is practical for specific scenes. Third, although IK constraints improve the final motion, it seems unnatural for some cases. We want to thank Yan Shangfu, Pico VR, Jian Su, Zhongwang Zhang, Rui Zheng, Si Yuan Wang for their support and help. And this research has been supported by National Key R&D Program of China. If you have any question, please send email to us. Thanks you.